Hello, this is Math 2270 coming to you from the College of DuPage during the summer of 2020, and the title of this lecture is First Order Differential Equation Systems and Matrices. Some of you may find the material in the book to be sufficient, but some of you may want some additional things, and so I would recommend going to the Learning Commons website, the Math Assistance Area section, and they have what is called Do-It-Yourself Reviews. And under the Pre-Calculus review, there is an excellent review of matrices, solved problems, and videos that you can look at, and it covers introduction to matrices, adding, subtracting, scalar multiplication, matrix multiplication, identity matrices, transposable matrices, determinants, inverses, solving system of equations using matrix inverses, and Cramer's rule methods. That's more than you would need for the balance of this course. By way of introduction then, recall that we did talk already in previous lectures about how to solve something that looks like this, where you had a system of equations that were differential equations in unknowns, and we had differential operators P11 of D operating on x1 and so on and so forth, x1 through xn, and this, we had these right hand sides, and the Pij are polynomials of various degrees in the differential operator. We did these by Laplace transforms, we did them by algebraic elimination, and we did them by kind of a determinant Cramer's rule approach. In this chapter, we're going to confine our studies to systems of first order differential equations that are special cases of systems that have the normal form. So you have a bunch of variables, x1 through xn, and you're taking the derivative with respect to t. You have that on one side, and then it's equal to stuff on the other side, which are functions of t, x1, x2, and through xn. Such a system of n first order equations is called a first order system. Now, first order systems are important in their own right, but also because any higher order differential equation can be written as a system of first order differential equations. And this will be our very next topic. So here is an example. I'm going to work through the example, then ask you to do one. So I want to write this second order differential equation as a system of first order linear differential equations. So we have 2y double prime minus 5y prime plus y is equal to 0. We have y of 3 is equal to 6, and we have y prime of 3 is equal to minus 1. So here's what we do. We start to write this with a simple change of variable, and we introduce two new functions. And the first one is called x1 of t, and we just let that be y. But then we let x2 of t be y prime of t. And now, if we differentiate both sides of these equations, I will get x sub 1 prime is equal to y prime, but y prime is equal to x2. So you see I have x1 prime is equal to x2. And x2 prime is equal to y double prime. But y double prime was our differential equation, so I can solve for y double prime, and I will get this is minus 1/2 y plus 5 over 2 y prime. But then y was x1 and y prime was x2. So now I have x1 prime is equal to x2, x2 prime is equal to minus 1/2 x1 plus 5 over 2 x2. And in fact, I can use these definitions as well to change my boundary conditions, not boundary conditions, initial conditions, so that I have x1 of 3 is 6 and x2 of 3 is minus 1. So when I put this all together, here is the system of differential equations, and you notice that it is a first order system of differential equations. I'm going to ask you to do example 2. I want you to write the fourth order differential equation as a system of first order linear differential equations. So we have the fourth derivative of y plus 3y double prime. Notice that we skipped the the third derivative, minus, this is sine of y, y prime, plus 8y equal t squared, and we have these boundary, not boundary, we have these initial conditions. You know what to do. Let's see how you did. Okay, we're going to do much like we did last time. We're going to say x1 is equal to y, but that means that x1 prime is y prime is x2. And we define x2, x3, and x4 this way. But when I take the derivative of this one, I get y double prime, that's going to be x3. The derivative of this one is going to be y triple prime equal x4. And the derivative of this one is going to be y to the fourth, which is what we had up here, so we can solve for that. So I move things to the other side, so it is minus 8y. Sine of t is times y prime minus 3 y double prime plus t squared, and you notice that that becomes, whenever I complete the substitution, minus 8x1 plus sine of t x2 minus 3 sine of x3 plus t squared. So the system of equations and the conditions after I've transformed them from y's to x's are these. So that's the answer you should have gotten. Now, many times we're going to be addressing these things in a matrix form of a linear system. So if, and these are bold to represent the matrix. So x is going to be my unknowns, and this is a column vector. So this is x1 of t, x2 of t, dot, 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 all the way down to x sub n of t. Capital A and bold-faced A of t is this matrix. Now these subscripts mean the one means first row and the second are columns. So this is first row, first position, second row, first row, second column, first row, nth column, second row, first column, second row, second column, second row, nth column. This is going to be nth row, first column, nth row, second column, nth row, nth column. And then I have an f of t, which is going to be a column vector again, which represents what will probably be my right-hand side, or at least we used to have it be a right-hand side. So the system of differential equations then look like this. I have a differential operator. I'm taking the derivatives of all these xt's. It's going to be the products of these, and reviewing the product, you're going to take this row times that column and add f1. So that gives you the first one. For the second one, it's going to be x2 prime. It's going to be this row times this column plus f2. And the last one is going to be xn prime is going to be this row times this column plus fn of t. Or simply, we can abbreviate it this way. Bold x prime is equal to A, the matrix, times x plus f. And if the system is homogeneous, its matrix form is x prime equals ax. That means that the f is 0. Let's convert some things to matrix form then. So I'm going to ask you to, here's a first order system of differential equations. Please change it to matrix form. You know what to do. Let's see how you did. If you work through, what you get is that the vector, x prime vectors sometimes are shown with a bar across the top, is equal to 4, 7, minus 2, 5 times x. Again, this is the column vector. This is a column vector. That's what you should have gotten. Let's do two more. You want to convert both of these. This is a problem we did before, a first order system, and this is another first order system. We did both of these before, and so I'd like you to convert these to matrix notation. You know what to do. Let's see how you did. This one is going to be the column vector x prime. It's going to be equal to 0, 1, minus 1/2, 5 halves, and this is what the column vector of the initial values will be. For this one, we will get x bar prime is equal to This is my matrix A times the column vector x, and I split off this because you see there's no x in this, so this is another column. And notice that I'm writing my initial conditions at 0 as this column vector, and that is what x bar is. Now for large systems, we sometimes will write this as x bar is equal to ax plus, and then this is going to be that f of t. We really already talked about that. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. God bless you all.